Hello everyone, Assalamualaikum. Welcome to my video. Today our topic is duality. It is a very important framework for understanding optimization problem as it connects different facets of decision making. It is a versatile tool that provides deep insights into economic behaviors and decision making process, offering both theoretical and practical benefits. For better understanding of the duality theorem, we need to make the concept of consumer's duality, hyperplane theorem and support function clear. So let's get started. Any consumer's decision has a dual nature. The consumer can either maximize his or her utility subject to a budget constraint or minimize his or her expenditure subject to a utility constraint. So this is basically the dual approach to the consumer theory. It will be more clear if we discuss the flowchart. We can see that consumer's duality has two problems. The first one is the primal problem. It means to maximize the utility subject to a budget constraint. It is also known as Marshallian demand or uncompensated demand. The another problem is the dual problem, which refers to minimize the expenditure subject to utility constraint. The dual problem is also called Hicksian demand or compensated demand. The optimal variables of the primal problem are price of goods and consumer's income. Taking these variables as function, we can get the indirect utility function. Similarly, we can get the expenditure function by taking the optimal variables of dual problem as a function, and the variables here are price of goods and utility. The interesting fact is that we can directly derive the Marshallian demand for good X from the indirect utility function by using Roy's identity formula. By the same manner, if we use Shepard's lemma, we can directly derive the Hicksian demand from the expenditure function. So this is the overall scenario of the consumer's duality. Now we will discuss hyperplane. In economics, hyperplane plays an essential role in convexity theory. Basically, a hyperplane is a flat affine subspace of a higher dimensional space. It is a mathematical construct that divides a space into two half spaces. Precisely, a hyperplane in n-dimensional space is a set of the form x belongs to R in n dimension such that p into x is equal to c. In a two-dimensional space, a hyperplane is a line, and in a three-dimensional space, it is a plane. That is, hyperplane is a subspace that has one dimension less than the ambient space and can be used to divide the space into two halves. Now let's talk about half space. A half space is a subset of Euclidean space that lies on one side of a hyperplane. A closed half space in Rn is defined as x belongs to Rn such that p into x is greater than or equal c. Geometrically, a closed half space is a set of points lying on or lying above the hyperplane. Now, there is a theorem named separating hyperplane theorem, which states that for every convex and closed set K, there is a half space or separating space. That is, there exists P belongs to Rn and C belongs to R such that P into x is greater than or equal C for all x belongs to K, and P into x bar is less than C for all the element outside of the set x bar belongs to K. Now our topic is support function. The support function of a set A is a way to summarize all the closed half spaces that include A. Specifically, for every non-empty closed set K subset of Rn, the support function of K defined for any P belongs to RL to be mu K of P is equal to infimum x of P into x for all x belongs to K and P belongs to Rn. When K is convex, we can reconstruct K from the knowledge of mu K dot. That is why the function mu K dot provides a dual description of K. We will see now how it happens. Notice that for every P, x belongs to RL such that P into x is greater than or equal mu K of P. It is a half space that contains K, and if x does not belong to K, then P into x is less than mu K P for some P. Thus, the intersection of the half space generated by all possible values of P is precisely K. That is, K is equal to x belongs to RL such that P into x is greater than or equal mu K of P for every P. Indeed, the support function mu k of p selects the element in K that minimizes Px hyperplane, which helps to make decision about optimization. Finally, we will discuss now the duality theorem. The theorem states that if K be a non-empty closed set and mu k dot be its support function, then there is a unique element in K, x belongs to K, such that for all price vector p, p into x is equal to mu k of p. That is, mu k dot is differentiable at p. Also, p into hpu is equal to e of pu. That is, e of u is differentiable at p. Moreover, derivative of mu k dot p is equal to x. To summarize, if the minimizing vector x for the vector p is unique, then the gradient of the support function at p is equal to x. Therefore, the duality theorem tells us that as far as the first derivative of mu k dot or the support function is concerned, it is as if mu k dot is linear in p. That's all for today. Thank you everyone.